Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Fiber optic cabling plays a crucial role in modern networks, especially in environments that require high bandwidth, long distances, or minimal signal interference. Among fiber types, there are two primary categories that you must understand to make informed design decisions: single-mode fiber and multimode fiber. Both serve the same basic purpose, transmitting data as light through a fiber optic core, but they do so using different technologies, with distinct advantages, limitations, and use cases. Knowing when and how to use each type is essential for proper network design and is a foundational element of physical layer networking knowledge. In the context of the Network Plus exam, understanding the differences between single-mode and multimode fiber is often required when interpreting infrastructure diagrams, selecting the correct media for a given scenario, or identifying the causes of signal degradation. You may be asked to recognize fiber types by cable markings, jacket color, or performance specs. You might also need to determine which fiber type supports a given distance, bandwidth, or transceiver configuration. These questions are not theoretical. They reflect decisions made every day in data centers, campus networks, and service provider environments. Single-mode fiber is designed to transmit a single light path or mode through an extremely narrow glass core. This precise core typically measures around 9 microns in diameter and is engineered to allow only one mode of light to pass through. The light used in single-mode fiber comes from laser sources, which produce a highly focused and coherent beam. This minimizes signal distortion and attenuation, making single-mode fiber ideal for long-distance transmission over many kilometers without requiring signal boosters or regeneration points. The characteristics of single-mode fiber make it a high-performance medium for both enterprise and carrier-grade networks. Its narrow core greatly reduces modal dispersion, the phenomenon where different light modes arrive at slightly different times, which can blur the signal. Because there is essentially only one light path in single-mode fiber, this dispersion is virtually eliminated, ensuring that the signal arrives with clarity even after traveling great distances. As a result, single-mode fiber supports significantly higher bandwidth and lower latency over long links than multi-mode alternatives. Single-mode fiber is commonly used in scenarios where distance and signal fidelity are critical. You'll find it in campus and metropolitan area networks, connecting buildings across a city block or a business park. It's also the standard for telecom carrier backbone networks, supporting links that stretch for tens or hundreds of kilometers. Long-haul ISP and cloud service provider infrastructures rely heavily on single-mode fiber to connect data centers across regions, countries, and even continents, often through buried terrestrial cables or submarine fiber routes. Multimode fiber, by contrast, has a much larger core, usually 50 or 62.5 microns in diameter, which allows multiple light modes to travel simultaneously. This means that the light can take different paths through the cable, bouncing off the cladding at various angles. The light sources for multimode fiber are typically LEDs or V-squels, vertical cavity surface emitting lasers, which are less expensive and easier to work with than the laser sources used in single-mode applications. Multimode fiber is optimized for short-distance communication and is widely used in local network environments. Multimode fiber offers several benefits that make it attractive for certain deployments. The cable itself is less expensive per meter than single-mode fiber, and the transceivers used with multimode, particularly LED-based ones, are significantly cheaper. Installation is also simpler in many cases, as multimode cables are more forgiving of slight misalignment during termination and splicing. However, these benefits come at the cost of distance and performance. Due to modal dispersion, the signal can degrade much more quickly as distance increases, especially at higher data rates. One of the key challenges with multimode fiber is modal dispersion. Because light travels through multiple paths simultaneously, these different modes can arrive at the receiver at slightly different times. Over short distances, this difference is negligible, but as the distance increases, especially beyond a few hundred meters, these variations start to overlap and distort the signal. This limits the total transmission distance and makes multimode fiber unsuitable for long-haul applications. The greater the number of light paths, the more pronounced the dispersion, and the more limited the cable's effective range. Multimode fiber is classified using OM ratings, which stand for optical multimode. These range from OM1 through OM5 and define modal bandwidth and supported data rates. OM1, 62.5 micron core, supports lower speeds over shorter distances and is largely obsolete. OM2, OM3, and OM4, all with 50 micron cores, provide progressively better performance, with OM3 supporting 10 gigabit Ethernet up to 300 meters and OM4 extending that to 400 meters. OM5, a newer standard, supports short wavelength division multiplexing, allowing multiple signals to run simultaneously at different wavelengths. These classifications help match the fiber type to the bandwidth and distance requirements of the application. A visual method for identifying fiber type is through the color of the cable jacket. In most structured cabling systems, yellow jackets indicate single-mode fiber. Orange jackets are typically used for older multimode fiber, such as OM1 or OM2. Aqua jackets signify laser-optimized multimode fiber, such as OM3 and OM4, which are common in newer installations. While color coding is not strictly enforced, it is widely adopted as a best practice to help technicians distinguish between fiber types during installation, testing, or maintenance. Matching the correct fiber type to connectors and transceivers is critical. Fiber connectors and transceivers are engineered to work with specific core diameters and light sources. Attempting to mix multimode transceivers with single-mode cable or vice versa can cause serious signal loss or failure. A single-mode laser light injected into a multimode cable may overfill the core, leading to reflection and loss. Similarly, using a multimode LED source with single-mode fiber will result in an underfilled core and weak or absent signals. Most transceivers are labeled to indicate the mode they support, and proper planning ensures compatibility throughout the link. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. One of the most important distinctions between single-mode and multimode fiber is the distance each type can support. Single-mode fiber is designed for long-range communication and can transmit data across distances of several kilometers without requiring signal regeneration. In many cases, single-mode links span 10 kilometers or more, with some advanced optical modules supporting ranges beyond 100 kilometers using optical amplifiers and dispersion compensation technique. This makes single-mode the preferred choice for wide-area networks, interbuilding connectivity, and telecom-grade backbone infrastructure. In contrast, multimode fiber is limited to much shorter distances due to modal dispersion. At slower speeds, such as 100 Mbps or 1 Gbps, multimode fiber can reach up to 2 kilometers using older standards like OM1. However, as speed increases, distance decreases sharply. For example, 10 gigabit Ethernet over OM3 OM fiber is limited to about 300 meters, while OM4 can stretch that to roughly 400 meters. These limits are not arbitrary. They result from the physical properties of multimode fiber and the nature of how multiple light paths create signal distortion over longer runs. Cost is another critical factor when comparing these two fiber types. Multimode cable itself is generally more affordable than single-mode cable, and the LED or vesicle transceivers it uses are significantly cheaper than laser-based modules. This makes multimode attractive for budget-conscious deployments where long distance is not required, such as in building links or connections between racks in a data center. However, for larger campus networks or metro-scale infrastructure, the lower cost of multimode transceivers may be outweighed by the limitations in reach and performance. Single-mode optics, particularly long-range modules like those supporting 40 GBS or 100 GBS over many kilometers, are more expensive than their multimode counterparts. This is due to the precision required to generate and manage a narrow, coherent beam of light using lasers. Installation costs may also be slightly higher for single-mode due to more stringent alignment requirements during splicing or connectorization. However, these costs are often justified by the long-term advantages in distance, scalability, and bandwidth that single-mode fiber provides. The underlying light source technology used in each fiber type significantly affects its performance. Multimode fiber employs LEDs or VCXLs that emit a wider beam of light with multiple angles of propagation. This broader launch angle leads to multiple light paths and consequently more modal dispersion. Single-mode fiber, by contrast, uses highly focused lasers that produce a narrow, single-mode light stream. This precision allows the signal to travel further with less degradation, and the reduced modal dispersion ensures that the signal remains clear over extended distances. Performance at higher speeds also reveals important differences between these two fiber types. As Ethernet speeds increase to 10 Gbps and beyond, the effective transmission distance over multimode fiber continues to shrink. For example, OM3 fiber supports 40 Gbps up to 100 meters and 100 Gbps over even shorter distances. Single-mode fiber, on the other hand, can support these high speeds over many kilometers, depending on the optical modules and link conditions. For networks planning to adopt higher speed technologies in the future, this scalability can be a decisive advantage. In data center environments, both multimode and single-mode fiber may be used, depending on the location and purpose of the link. Multimode fiber is commonly deployed for short-distance connections within a single row or between adjacent racks. Its cost-effectiveness and compatibility with low-cost transceivers make it ideal for top-of-rack to end-of-row switch connections. Single-mode fiber is often reserved for longer-distance links, such as connections between distribution switches on separate floors or in different buildings. Many modern data centers deploy both types, using multimode for inter-room cabling and single-mode for inter-building or core connectivity. Using the wrong fiber type for a given application can result in serious connectivity issues. If a single-mode transceiver is connected to multimode fiber, the narrow laser may overfill the core, causing reflections and excessive loss. Similarly, connecting a multimode LED transceiver to single-mode fiber results in an underfilled core and poor signal coupling. These mismatches often lead to dropped packets, high error rates, or a complete lack of link negotiation. Identifying such mismatches requires the use of fiber testers, light meters, or simply checking the transceiver and cable markings. Each fiber type plays a role in different network layers based on their capabilities. Single-mode fiber is often used at the core or distribution layers, where long-distance, high-capacity links are required. These include building-to-building connections, metro rings, or connections to cloud and ISP infrastructure. Multimode fiber is commonly used at the access or aggregation layers, where switches or servers are clustered within a limited physical area. Understanding how fiber mode maps to network function helps inform both design decisions and exam answers when selecting appropriate media for a scenario. For the Network Plus exam, expect to encounter fiber mode questions in a variety of forms. You may be asked to identify fiber mode by jacket color or connector label. You might be presented with a scenario involving a data center upgrade and asked to recommend a fiber type based on performance and distance requirements. Diagram-based questions may show cable paths and transceiver specifications, requiring you to match the correct media type. Having a strong command of the physical characteristics, performance limits, and cost differences between single-mode and multi-mode fiber is essential for success. In conclusion, understanding the differences between single-mode and multi-mode fiber is key to mastering fiber optic networking. These two types of cable are designed for different purposes: single-mode for long-distance, high-bandwidth connections using lasers, and multi-mode for shorter, cost-effective links using LEDs or VCSELs. Differences in core size, light path, modal dispersion, and transceiver compatibility make choosing the correct type critical for performance and reliability. Whether you are designing a data center, planning a campus backbone, or preparing for the Network Plus exam, the ability to differentiate between fiber modes and select the right one is an essential skill for any network professional. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.